So in this part, let's talk about how we actually find the steady state to a regular Markov process. Let's just try to remember what we have so far. We started here with P naught working, not working, and this was back in the 60s where 40% of women worked and 60% did not. Then we generated P1, and we got P1 by this, T to the first, P naught, and out of that one we got 50%, 50%. And then we generated P2, and we got P2 by taking the transition matrix, squaring that times P naught, and that gave us this 55%, 45% vector. A vector is just a matrix with one row or one column. Then we went and we got P3, which was T cubed, right? Remember these match, of P naught, and that gave us this 0.512.488. So the pattern looks like this, right? If we want any particular p-value, we'd raise the transition matrix to that power and then multiply it by the initial state. So let's talk about getting this steady state. So steady state, we don't know what it is right away, right? We don't know. Like, look down here. This is a regular transition matrix, so it's going to reach a steady state. And it looks like, okay, what do? We started at 40%. Went up to 50, went up to 55, went up to 51.2, so it's the percentage of women working is increasing, but that increase is slowing down. If we just kept going, what would we expect this number to be? And what would we expect this number to be? Well, right now we don't know. But here's what we do know, that if I want to get to the next state, say I want the next one, all right, then if I take the transition matrix and apply it to this steady state vector, where should we be? Well, it's the steady state. So do you agree that we should be right back at the steady state? Right, if we're currently here at the steady state, right? So imagine we're at the steady state. That means things don't change. And then we go to the next generation, right? We apply a transition to it. Well, if we're at the steady state, there should be no change. So that's going to be our equation for getting the steady state. It's a matrix equation. So for our example with this transition matrix, let's get the steady state. So what we're going to do is we're going to take our transition matrix, 80, 20, 30, 70, and apply it to the steady state. Right? We don't know what those numbers x and y are, but we do know that since x and y represent the steady state, when we make a transition, there should be no change. So there's our matrix equation. And from this matrix equation, we can get a system of equations, right? We're going to multiply. Remember how to multiply matrices? Over and down, right? First and first plus second and second. So we're looking at this, 0.80x plus 0.30y, and down here, right, second row, first column, first and first plus second and second. So this is going to be plus 20x plus 0.70y, and that's equal to this matrix here, xy. But now two matrices are equal when their corresponding components are equal. So this component must be equal to that one. This one must be equal to that one. So we'll write that. We'll get, if I can write it here, we'll get 0.80x plus 0.30y, that's equal to x. And then 0.20x plus 0.70y, that's equal to y. There's a system of equations. And we can solve this system and hopefully get the values of x and y. But you know, when we solve a system like this, what we like is we like all the variables on one side and all the constants on the other. So I want all the variables here on the left side and the constants on the other. So how about if we do this? Let's subtract x, we'll subtract y. Okay, so be a little bit careful when you do this, because what we're going to have here is this. We're going to have, I'll write it all out. We're going to have 0.80x minus x, and then plus 0.30y. That's going to be 0, right? X minus x is 0. And in the second equation, we're going to have 0.20x plus 0.70y, and then minus y, right? We're going to subtract that y. That's going to be 0. Now, what do we get here? What is this part right here? 0.80x minus 1. So it's like 0.8 minus 1, or 80 minus 100. So be careful when you do this one here. This is going to come out to be negative 0.2. Let me get that all in the same color here. This is going to be negative 0.20x plus 0.30y equals 0. And in the second part, we have the 0.20x. Okay, there we go. 0.20x. And then what do we get here? Well, we're at 0.70 minus 1, right? 70 minus 100, if you like. 0.70 minus, or 0.7 minus 1. 0.7 minus 1 is negative 0.3. So we get negative 0.30y equal to 0. Now, you see what this is? Look what we've got here. We did this long ago when we first started studying systems of equations. You see the second equation? How does it compare to the first equation? It's really just the first equation multiplied through by negative 1. So these are not two independent equations. The second equation is just a multiple of the first equation. So what happens here is that there is no unique solution. You remember that? So there's no unique solution here. So we have to come up with something else in order to solve this. So here's our way out of this dilemma here. Let's go ahead and stick with the point 20x plus 0.30y equals 0. But what I'm going to do is I'm going to eliminate this equation since it's not really an independent equation. But if I have two variables, I need two equations. I've got one, right? We've got this one. We thought this was another one, but it wasn't. It was just a multiple of this one. So we have one equation. I can get another one, an independent equation, with this known fact, right? Here's what we know. We know that if we add x and y together, we get 1. So x plus y is equal to 1, right? Now remember back here, these are probabilities. So if you add x and y, you get 1, right? You add down the columns, you always get 1. So there's our new system. So all we're going to have to do is solve this system. And I'm going to do that on my calculator. So if we solve this on the calculator, we go into matrix A and input just the coefficients, right? Negative, well, let's put in negative 0.20 or negative 0.2, 0.30, and 0. Just coefficients, 1, 1, and 1. And then what we do is an RREF on this matrix, negative 0.20, 0.30, 0, 1, 1, 1. Do an RREF on that. And when I did it, I got this matrix right here. I got 1, 0, right, 0, 1. We know we're going to get that. And then I'll just put the line in because I know I get that. But then for my solutions, I got this. I got 0.6 and 0.4. And sure enough, those numbers, if I add them up, they add up to 1. So I think I'm good here. So what I'm going to conclude then is that my steady state is going to be this, right? My x and y is going to be 0.60 maybe and 0.40. So the steady state is working, not working. So in the long run, if everything stays as it is, we'll have 60% of women working, 40% not working. So if we just retrace what we had, we started off with the mothers in the 60s being at 40% working, 60% not working. Then for their daughters, the next generation, make a transition from one generation to the next, it went up to 50 and 50, right? Up to 50, down to 50. And then the granddaughters, well, working went up to 55, not working went down to 45. And then in the great-granddaughters, we had 575 and 425, ... If we just keep going, we're going to say if we go out long enough, it's going to be 60% working, 40% not working, and it's just going to stay the same after that. It won't change. From one generation to the next, it's going to be 60-40.